We have almost solved the Poiseuille's problem, determined the velocity profile, and we were looking at the shear stress. So one or two additional observations on the same, that the viscous shear force per unit area acting on the wall will be determined by the force divided by area, because that is the definition of force per unit area, and if we calculate in our terms, it will be equal to this, where r here is the radius of the pipe and the dp by dx is the external pressure or pressure gradient that is being applied. I is the unit vector in the x direction. The direction of this force, of course, agrees with our intuition. You will see this comment is because of the negative sign that is appearing here. And du by dr is equal to 0 at the center, that is where r is equal to 0. And therefore, at that place, tau of rx will also be 0, and that is why, so there will be no stress either right in the middle, right on the axis of the fluid flow. Geometrically, it can be shown in this manner. And so all the particular things that are variables that are being shown in a control volume that has been arbitrarily chosen from within the fluid flow. So this completes the solution more or less. So far, all our Navier-Stokes equation that we discussed, about 3 or 4 problems, in these problems, they were considered for steady motion. That is, all partial derivatives with respect to time rendered 0 value, and we ignore them. And that also simplified the problem for us, because if the flows were unsteady, it means another partial derivative would exist in the equation and it will be non-zero. Therefore, when integrating, it means we have to determine that also, that term as well, which is being differentiated with respect to time, and we have to determine its value, thus creating a level of difficulty. But however, the solution, there are ways of finding solutions for simple enough problems that are unsteady in motion. We will consider 1 or 2 such examples